Leaving Cert Higher Level 2019, Paper 1, Question 2. So this one says the graph of the function f of x equals 3 to the power of x, where x is a real number, cuts the y-axis at 0, 1, as shown in the diagram below. Alright, so here's the graph of it between minus 0.5 and plus 2.5 on the x-axis. Now, in A part 1 here, it wants us to draw the graph of the function g of x equals 4x plus 1 on the diagram. So this function here is a linear function. Unlike this one, which is a curve, it's non-linear. This one is linear because you can think of g of x as y. So I could write that function like so. Y equals 4x plus 1. And that's now in the form y equals mx plus c. It's a line. Now, if I want to draw the graph of a line, I don't need multiple points like this curve has. All I need are 2 points. So I'm just going to get 2 points here and then draw a line through them. And that's going to be g of x plotted. So I'm going to take 2 random values of x and then sub them in. So generally the further apart they are, the better. But I might just go here with 0 and 2. So let's find out what y is when x is 0. So when x is 0, let's see what y is going to be. So y, just replace x here with 0. So y is going to be then 4 by 0 plus 1. Now 4 by 0 is 0, plus 1 is 1. So 1 point then is going to be 0, 1. Now, so I'll plot that in a second, and then let's sub in, say, 2. So when x is 2, again you're going to replace x here with 2. So y is going to be 4 by 2 plus 1. And that is going to equal 9. So your second point then is going to be 2, 9. So 0, 1, well, 0, 1 is actually the same point as that. So that's going to be 1 point on my line. And the other point is 2, 9. So 2, 9 is actually that point there as well, as it happens. So we've chosen the 2 points that lie on the curve as it happens as well. So all we now have to do is draw a line through those 2 points. So you'll be getting a ruler here and just drawing a line through them both. So I'll try and do that now. So yeah, it's going to look something like this. So that's going to be g of x. Alright. Okay, that's all you need to do. Just get 2 points on it to draw a line. Right, that's A part 1. Now A part 2 says use substitution to verify that f of x is less than g of x for x equal to 1.9. Well, f of x here is 3 to the x. So f of x is 3 to the x. And we know as well that g of x is, there's that function we had a second ago, 4x plus 1. So all we've got to do here really is just, get f of 1.9, get g of 1.9, and just verify that f of 1.9 is less than g of 1.9. So f of 1.9, all we have to do here is replace x with 1.9, so it's 3 to the power of 1.9. 3 to the power of 1.9 on the calculator will give us, right, okay, so to 2 decimal places is going to give us 8.06. Alright, and then let's sub in 1.9 into the other function, so let's get g of 1.9. So g of 1.9 then is going to be 4 by 1.9 plus 1. So 4 by 1.9 is actually 7.6, plus 1 is 8.6. So 8.6 is greater, of course, than 8.06. Therefore, we can conclude that yes, f of 1.9 is indeed less than g of 1.9, which is another way of saying what they've said here. F of x is less than g of x for x is equal to 1.9. Alright, and just going back to the diagram here, when x is 1.9, which is up here somewhere, we can see that the curve f of x is slightly less than g of x, is slightly lower for that particular value of x, 1.9. But they wanted us to do it using substitution, using algebra really. Right, so moving on to part B, it says prove using induction that f of n is greater than or equal to g of n, where n is greater than or equal to 2 and n an element of the natural numbers. Right, so really it's wanting us to show that for any value of n greater than 2, f of n is now going to be greater than or equal to g of n. So yeah, so we can see here that, judging by our diagram here, for values of x greater than 2, it looks like f of x will be greater than g of x. But they want us to prove it's the case using induction. So there's a bit of work to this. Now I did a solution to this out already, so I'm just going to show this now on the screen. So yeah, so they want us, the question really is to prove that f of n is greater than or equal to g of n for n greater than or equal to 2 and n an element of the natural numbers. So really what they're asking us to show is that 3 to the n is greater than or equal to 4n plus 1, as long as n is greater than or equal to 2. So with proof by induction, the first thing you've got to do is show that it's, or just demonstrate that it's true for the first value of n. Usually that's 1, but here it's actually 2. So all you have to do here is we're going to say show true for n equals 2. So we're going to replace n here with 2 and n here with 2 and just verify that that inequality is satisfied. So 3 squared hopefully is greater than or equal to 4 by 2 plus 1. So 9 is greater than or equal to 9. That is true. Therefore, this is true for n equal to 2 at least. But is it true for all values of n greater than 2 as well? So that's our next job. So we're going to assume it's true for an arbitrary value of n, which we're going to call k. So we're going to take it as a given that we're going to assume that this is true for a particular value of n, which we're going to call k. So we're going to assume that 3 to the k is greater than or equal to 4k plus 1. We're going to take that. We're going to just take that. We're going to put our faith in that. Now, so using this assumption, we will now show it is true for n equal to k plus 1. i.e., we've got to show that, we're going to be replacing n here with now k plus 1. So our job now is to show, using this assumption, that 3 to the k plus 1 is greater than 4 by k plus 1 plus 1. Again, I'm just replacing n here with k plus 1. Now that there can be broken into 3 by 3 to the k, using a law of indices. So our job is to show that 3 by 3 to the k is greater than or equal to, and just multiplying this out, we're going to get 4k plus 5. So our job now is to show that that is true. Now, with proof by induction, you're always going to have to use your assumption. So sometimes you use it at the start, other times you use it later on, but I'm going to use it here at the start. So I'm going to take my assumption here. So I've said here, from our assumption, we know that 3 to the k is greater than or equal to 4k plus 1. So again, as far as we're concerned, that's true. So if I multiply both sides of it by any number, in this case 3 I'm multiplying both sides by, it'll still be true. So I know that 3 by 3 to the k is greater than or equal to 3 by 4k plus 1, i.e. 3 by 3 to the k is greater than or equal to 12k plus 3. So I know that's true. So I know that's true, but really I'm trying to prove that. I'm trying to prove that 3 by 3 to the k is greater than or equal to 4k plus 5. I know it's greater than 12k plus 3, but I want to know, is it greater than 4k plus 5? Well, so now the question arises, if I know that 12k plus 3 is greater than 4k plus 5, and I know that 3 by 3 to the k is greater than 12k plus 3, then this 3 by 3 to the k has got to then be greater than 4k plus 5. So the question now is whether that there 12k plus 3 is greater than 4k plus 5. Let's see, is it? Yeah, so as I've said here, if we can show that 12k plus 3 is greater than or equal to 4k plus 5, then we've shown this is true. Okay, so yeah, so I've posed the question here, is 12k plus 3, is it greater than or equal to 4k plus 5? So it will be if, so what I'm doing here, I'm bringing this term over here, making it a minus, and bringing the 3 over here, making it, well, changing its sign as well. So it will be if 12k minus 4k is greater than or equal to 5 minus 3. In other words, it'll be true if 8k is greater than or equal to 2. Dividing both sides by 8 there, it'll be true as long as k is greater than or equal to a quarter. But in this case, n is greater than or equal to 2. Now k is a number that I made up, but it has to take the same values that n takes. So if I know that n must be at least 2, then k must be at least 2. Now I know this, by the way, is true as long as k is greater than a quarter. Now in my case, in my question here, k must be at least 2. Therefore it's certainly greater than a quarter. Therefore for all values of k that I'm interested in, that's going to be true. So I know now that for any value k that we're interested in here, 12k plus 3 will be definitely greater than or equal to 4k plus 5. So now I can conclude that yes, 3 by 3 to the k is indeed greater than 4k plus 5. Alright, because again, just to reiterate there, I know that's true there. The question was whether that was true. So I know that 12k plus 3 is greater than 4k plus 5. And if 3 by 3 to the k is greater than that, and that in turn is greater than that, then of course 3 by 3 to the k is definitely greater than or equal to 4k plus 5. So now that's what we had to prove. So now we know, so as I've said here at the end, so hence f of n will be greater than or equal to g of n for n equal to k plus 1, as long as it's true for n equals k, because we used an assumption there. We assumed that this was true, right? So, but we now know that if it's true for n equals k, it will be true for n equals k plus 1. So, as I've said here, hence if it is true for one value of n, it will be true for the next. So that's the breakthrough when it comes to proof by induction. Your job really is to show that if it's true for one value of n, it will definitely then be true for the next value of n. But as I said here earlier, we showed it was true for n equals 2. So if it's true for n equals 2, I know it's going to be true for n equals 3. And if it's true for n equals 3, it's going to be true for n equals 4 and 5 and so on. And all n greater than or equal to 2, n an element of the natural numbers. Okay, and that's question 2 completed.